think it's 1 p.m. Eastern. We can slowly start. A lot of people are getting admitted and joining, but we can slowly start. First of all, let me thank everybody that joined today. Today presenters, let me introduce today's presenters, and he can take it over with this very exciting presentation. So today's presenter is George Stefopoulos. He's the Director of Advanced Grid Innovation Laboratory for Energy at the NYPA, the New York Power Authority. He has been with NYPA since 2009, initially as a research and technology development engineer, and then as NYPA's Smart Grid Solutions Architect. He's a senior member of IEEE and an associate member of IET. George received his diploma in electrical computer engineering from NTUA, National Technical University of Athens in Greece, and he holds a master and PhD degree from Georgia Tech, as well as an MBA degree from Pace University of New York. Today's presentation from George Stefopoulos will be on the development of a cyber-physical testbed in an electric utility environment. And without further ado, George, please go ahead and let us know about this very exciting topic and this presentation. Questions, you can pose your questions at the chat, or you can answer your questions later on at the end of the presentation.
Thank you very much, Harry, and good morning or good afternoon, everyone, depending on where you are. I'm very pleased to be here, and thanks very much, Harry, for the invitation to give this presentation in this forum. What I'm going to talk about today is at a high level a description of various activities that we do in the New York Power Authority, looking into developing R&D type of test bed that we can use with the end goal to invest more in new technologies, test new technologies, and promote new technologies. We call that initiative, and this is a fairly recent initiative that, although it started several years ago as a conceptual idea, it was implemented recently. We call this initiative Advanced Grid Innovation Laboratory for Energy, or short AGILE. And it encompasses a lot of different capabilities, and it has a fairly ambitious vision that I'm going to talk about. My presentation is going to be fairly high level, and it's going to be more to introduce everybody to how New York Power Authority is seeing several aspects of this topic and what are the various activities that we are doing. I must also mention that it's quite interesting that these are activities that others have been engaged in, and there will be fairly few similarities with the initial presentation of this series that Dr. Nandwan did from Lawrence Livermore National Laboratory. So I will present similar approaches and similar concepts, but from an electric utility perspective. Before I start, and I hope everybody can see my screen well, just a quick overview. I'm going to give you a couple of minutes overview about what New York Power Authority is. Many of you may not be familiar with it, and many of you might not even be from the US, so you may not be familiar with NYPA and its activities. I'll talk a little bit about what this Agile Lab is and how it evolved and what are the current capabilities, and focus a little bit more on the topic of the presentation, which looks about specific cyber-physical testing and capabilities that exist in the lab. And finally, I will conclude talking a little bit about what our future plan is and the future direction for this initiative. So a little bit about the New York Power Authority. Overall, it is a governmental organization. It belongs to the state government of New York. It was established quite a long time ago in 1931, and it is the largest state public electric utility in the United States. The areas that we do business in are generation and transmission. So we do wholesale power generation for the New York State, and we also, of course, export to neighboring states. We do provide about 25% of the total New York State generation. What is pretty interesting, however, is that we do not have a distribution system. So although we are a transmission owner and we own transmission, we don't have a distribution system, and therefore we don't serve customers. We do have customers that are contractual customers that buy power from us, and these are typically large scale customers, either commercial customers, industrial customers, other governmental entities, but we do not serve them directly. They are served by the local distribution utility. Another interesting thing is that we do own transmission. We own about 1,400 circuit miles of transmission, but all is at high voltage level, essentially 230 kV and above up to 765 kV, and they comprise the backbone of the New York State grid. Another peculiar fact about us is that although we do own the backbone of the New York State transmission, we don't have a service territory. So our assets are scattered throughout the state, and that makes it a little bit challenging to see ourselves as any traditional utility would see themselves. That is, they have a control area that they control, they have their own assets that they fully control. In our case, and I'll show you two pictures in the next two slides, our assets are scattered throughout the state. In terms of generation, we are primarily hydro entity. About 80% of our generation in terms of energy in 2019 was hydro, and the rest is gas. And from a business perspective, we are a governmental entity. We're a non-for-profit entity, and we support our own operations. Just to give you a quick idea in terms of generation, our main generation is hydro, and it's three major large hydro plants. One is near Niagara Falls in New York. The other is near St. Lawrence River in the northern part of New York. And another plant that is worth mentioning is a very large-scale pump hydro facility that we own in the central New York, which is over 1,000 megawatts. That is one of the largest hydro facilities, pump hydro facilities that exist in the US. In terms of transmission, like I mentioned, yes, we do own the backbone of the transmission grid, mostly 345 kV, 765 kV, and 230 kV, but we're scattered all over New York State. So this provides a challenge that we do have lines, for example, that we don't own the substations that the lines terminate to. We do have lines that exist in other people's service territory and they connect to other people's lines. So many of the activities that you typically see in an electric utility are not easy for us to do because we don't own a territory that we fully control. And that poses some of interesting challenges, especially if we're looking about deploying new technologies, taking advantage of new technologies. That means that we always need to coordinate and do things in partnership in many cases with other entities in New York that own the rest of the transmission grid in New York. And also please keep in mind, New York is a market environment, so we do have independent power producers and the grid is owned by 7 transmission owners. So having said that, let me build a little bit the case for what I'm going to talk about. As everybody is aware, recent years there have been major changes that are taking place in the electricity grid, primarily looking into changes that are happening because of customers' demands. There is a clear turn towards cleaner energy in terms of renewables that are being constantly integrated into the grid, and the US is picking up a lot on this as well. There are increased resiliency and reliability requirements that are coming up, and a lot of these involve new technologies being embedded into the grid. I mean, we typically talk about smart grid, and that's a very generic term, but in reality, these new technologies that are constantly being incorporated in the grid essentially make this interdependency between physical aspects and cyber aspects much more tight and much more of a value to be better understood and further investigated. So looking into how we better explore and invest in new technologies, about 5 years ago, the New York Power Authority started some large-scale strategic initiatives that look into the infrastructure modernization of our assets and of the New York State grid overall. Again, being a governmental entity, in many cases, we look things broader than just our own company. We also play a role into improving the way the New York State grid operates overall. So one of the ideas that came up and moved actually into implementation is this Advanced Grid Innovation Laboratory for Energy, which essentially it is a laboratory facility, but we are looking from it from a broader perspective than just a lab. So the idea of this environment came up many years ago, but we spent a lot of time thinking about it and exploring what exactly we want to implement in a lab like this. The key idea and the key differentiation between potentially other labs that exist in academia or other utilities is that we don't want to view this as a New York Power Authority lab that NYPA uses for its own purposes, but we're looking at it as a collaborative environment that can bring together stakeholders from across the industry and academia, that they can work together to develop new technologies and, most importantly, accelerate that development and adoption of new technologies in the actual grid. I mean, one item that we clearly saw when we started this journey was that, contrary to other industries, that a new idea or a new technology finds its way from inception to being a commercially available technology pretty fast. In the electric power technology or electric power systems industry, this is a long journey. So that we have ideas that were initiated or were conceived and thoroughly investigated from an R&D perspective even 20 or 30 years ago that now start finding their way to actual grid operations. So this was something that we thought, if we can do something to bridge that gap or to some extent make that gap shorter, that would be something of value. So we see this environment that we're putting together as a collaborative environment that we can work with other partners. Other partners could be utilities, universities, national labs in the US, other organizations. It can include other strategic partners that we can have relationships with. It can include technology developers. This could be like companies that develop new technologies and they want a testbed to test and try these technologies. Or it could be academic institutions that do research and they want a realistic testbed to test and demonstrate the value of these technologies. And by bringing all these people together, we feel that there is significant value established in a center of this nature. Looking into the capabilities of this center, we focused on 5 pretty broad areas, and all of them actually do provide this interdependence between physical and cyber systems. So starting from advanced T&D applications, grid automation, sensors, power electronics, and cybersecurity itself, we wanted to create these capabilities and these areas within that lab in a gradual way and expand them as we see valuable and fit. But one other aspect that we brought in as in the center of all of this is the capability to provide a simulation and modeling environment that could serve all these other areas of research. And as I will explain more there, the real-time simulation environment is where we started with and where we saw the most value going forward. The vision for this facility and for this lab is that it can be a venue that essentially provides value to a lot of stakeholders. And some of the key areas of value that we see is we want to establish something that can be used for specialized studies or support R&D work, focusing on powerful modeling and simulation tools, with the expectation that this could be used as a testbed to integrate new technologies into the grid. Again, like I said, we did invest quite a bit and we decided to move forward with hardware, with real-time simulation capabilities for various systems. So most of you are familiar with those, but we do have significant capabilities both in RTDS and the operator simulation platforms, and use this for testing and demonstrating equipment capabilities. One of the key differentiations, which again, we feel it is important, is that we wanted to create an environment that operates based on actual data and models. So we're not looking into using potentially synthetic data or potentially test models. We're looking into developing actual models of the New York State grid and provide also actual measurements for the grid and use this data to do any research that we do. So the idea again was that this is a center that potentially somebody would like to demonstrate the value of a technology on the New York State grid and use that lab to essentially accelerate the way this technology can find an actual application to the grid. So this is a pretty challenging task. Again, there are a lot of constraints about using actual data, actual models, and even collecting this, but this is our vision. Finally, another thing that I already mentioned is we see it as a collaborative environment. We don't want to tie it only to the operation of our company. We want this to be a facility that others can come in and do work with us and utilize the resources that we put in place. And for anybody who want to demonstrate something for the grid of New York, we feel that this could be like the venue that you can do that, reaching out to all the New York utilities there, because we consider all of them partners in this endeavor. Now, talking a little bit about how this evolved, this is the vision for where we want to end. We took everything in stages though. So instead of trying to go full blown and build this facility, we started with something smaller scale, which we call a proof of concept type of lab. And this is where all activities concentrate now. So we did build a small scale lab that started with focusing on real-time simulation capabilities in our headquarters facility. And we try to operate this lab according to that vision, meaning doing collaborative projects with others and trying to establish what value we can get out of this lab. If we do that and we see that there is value in specific areas and we get enough interest from external stakeholders as well, then we will make a decision to move to the full-blown new facility that we're looking into putting in place. So we started with something small that still has a lot of capabilities and can provide value. And then the vision is that if there is interest from others as well, we can move on to something more substantial. Now, what are the current capabilities that we invested in as a starting point? Real-time simulation is what I already mentioned, focusing on hardware and software in the loop capabilities, because that gives us the most flexibility and getting the most value out of the real-time simulation. And one other aspect that we added, which again ties well with the discussion of this task force, is can we also simulate other systems that have interdependencies with the power grid and use this as part of our test bed. So we did invest also on simulation of communication systems and cybersecurity events. Finally, there is one more capability that looks into potentially economical evaluation from potential new technologies or technical solutions, but this is a little bit outside the scope of this presentation, so I won't focus too much on this anymore. Now, going further, again, many of you are probably familiar with all this, but just talking a little bit to why we see the value of this hardware and software in the loop capabilities. First of all, the way we envision the test bed is that we do have a real-time model of the power grid, and we have been looking into developing, and that's a lot of the effort that we have put in place to develop a real model of the New York State grid and make it available in the lab. Then the way we see it expanding is that now with the software and hardware in the loop capability, we have the capability to bring in equipment that can be interconnected with our simulators, and then this can be used for testing the equipment or evaluating the performance of this equipment. And this interconnection can be done either via regular communication protocols that exchange data between the systems or via analog signals, of course. Now, one other value that we can see in real-time simulation is this co-simulation capability. And by co-simulation capabilities, there are two ways to see it. One is across multiple domains, and that I mean you may want to co-simulate, for example, a transmission grid with a distribution grid at the same time. As well as multiple disciplines. And that's kind of like something that is of more interest, alluding back to what I said earlier. So simulate a grid with a communications network, or a power grid with a gas network, or any combinations of this nature. So at the initial stages, we focus more on the communications network and how we can build capabilities to essentially emulate a grid model, and at the same time with a communications model, and use this as a basis for the test beds that we're building. So what are the components of these test beds and what components we have actually brought in the lab? One quick note that I will make here is keep in mind this is all work in progress. This lab was established like about 2 years ago, and we're still in the process of building all of this. So in many cases, it seems that we are trying to build a lab and at the same time use it as well. So the first component is, again, the virtual grid. So build an accurate model of a grid that is realistic and can be used as a test bed that provides value and can show that something will work in practice. So that's the part that we are doing, and we have spent most of our time here creating a model both in the EMT domain, as well as, of course, in the phaser domain, as many simulators have both capabilities, that represents the New York State grid. The second piece is the communications network, and for this, there are quite a few systems available that can do that. We did invest in a commercially available tool for this, and we implemented it in the lab. And the idea is that, again, we will be using this tool to build connections between grid nodes and emulate the communication networks between the grid nodes that we want to exchange data, therefore creating the complete cyber-physical system, for lack of a better term here. The third component is the cyber assets. So bring hardware in the lab that they can essentially represent hardware that can be found in a typical substation. And this hardware now can be interconnected with both the grid emulator and the communications emulator, and create test beds that could represent an actual substation environment. And the last thing that we brought in, and we are building some capabilities, is monitoring systems. Can we use existing monitoring systems that we may want to evaluate or test to monitor these test beds that we are building, and create now a complete set that not only simulates but also monitors a complete grid of this nature. So looking into potential applications that we are looking into and test beds that we are building, in terms of emulation software, grid emulation, I already mentioned, building an electromagnetic as well as electromechanical model of the New York State grid. And this is what we use as our grid test bed. From the communications aspect, like I mentioned, we did invest in an actual commercial tool that gives us the capability to investigate events now that are happening on the communications domain. So if we do have a model of the communications grid, then we have the capability to create scenarios that would involve failure of specific equipment, the communications that will require rerouting of traffic. We can also emulate specific attacks on the grid. There are cyber capabilities that software include, and therefore see how this attack affects the communications network. But in all these cases, the end goal is not only to evaluate the aspect of it on the communications grid, but also see how events on the communications layer affect the operation of the actual electric grid layer. The next item that I mentioned, and I'll elaborate a little bit more, is this hardware small-scale substation testbed. So we did work quite a bit with our cybersecurity group, and we're still working with them to bring in equipment that is representative of what we could have on our substations. Let's say it could be RTUs, it could be relays, it could be other control devices, and create local small-scale replicas of this substation and create traffic that is exchanged either locally within a substation or between substations, injecting a communications grid model in between them. And therefore, this can now be used as a test bed to test any of the things that I mentioned earlier: equipment failure, a cyber attack on the network, potential attack on a specific piece of equipment, a firmware corruption of an equipment, and see how this will have an impact not only on the cyber part of it, but also on the grid side of it, since this device is supposed to be controlling some function on the grid. And the last piece that we are working again with our cybersecurity group, and they are taking the lead of this, is evaluating specific monitoring systems and potentially new ideas and new technologies on cyber monitoring systems, and see how well they can monitor a communications grid, or how well they can detect anomalies or detect intrusions into that grid. One other aspect that we are doing here is that we're not only using the simulated networks as a test bed, but for these network monitoring systems, we're actually using the entire lab network as a living lab. So some of these systems also monitor the entire lab traffic, and the traffic can include the traffic that is ICS type of traffic from industrial control systems between test beds, as well as the actual IT traffic of the lab. And this essentially is using, like I said, the actual lab environment as a living test bed. Now, this is just an illustrative example of what we can do, just to give you an idea of how the modeling could work. This doesn't really represent anything realistic, but it is an approximation of some of our PMU networks that we have. So this essentially is a simple network model that shows PMU and SCADA traffic running from a couple of substations down to a control center. And again, the idea is that by running different simulations, you can extract information about how well your network performs. So in this particular example, this is the normal simulation that shows, for example, in one of the nodes, there are 3 packets that were lost during a 1-minute simulation that was run. And the next graph shows approximately the average delay on the network, which is maximum on the order of 55, 60 to 70 milliseconds. Now, again, running scenarios on a grid like that, like you can run an attack or a denial of service attack on one of the nodes, you can immediately see the impact that it has on the traffic. So we can see, for example, that the number of packets that were lost increased from 3 to more than 200 on several nodes of the system. And these are the nodes that are mostly affected by the attack. And you can see also that the average delay increased almost twice. So we can see delays now that are up to 200 milliseconds or more. Now, unless you are interested in the communications network design and the performance, this by itself is of some value, but not of total value. The idea now is, how does this affect the performance of the grid and specific control schemes that may be running using this data that is flowing on the communications grid? So for this, that's kind of like the overall architecture that we see implementing in the lab. And that is quite flexible and generic to essentially accommodate a variety of use cases that we can run. So again, we have the grid emulation in one piece, real-time simulation of the New York State grid model. This is essentially the base for the simulation. You can generate any data you want from there, or any data that is of interest, and then connect the hardware devices in a hardware-in-the-loop environment to this network, either via analog signals or via any other communication protocol. For example, 61850 sample values could be one of them. Then these devices are acting as the monitor devices of the system. These now send their traffic. They are interconnected to the grid, to the communications grid emulator. So this traffic now is routed through a realistic, again, network model of the grid that we're trying to use in our example. And this traffic could be, again, any type of traffic, SCADA type of traffic, PMU traffic that runs on the network from various sources to various destinations. This traffic then can be exported to a concentrator. In this particular instance, I have a Phaser data concentrator, but it could be any concentrator depending on the traffic that is being implemented. And then the idea is that this data now is used as input to a wide area control scheme, or it could be a local control scheme if there is remote data needed for a local control scheme. And this, in a closed loop setting, again controls the grid. So now this complete environment gives us the capability to see, okay, if I have disturbances on the grid, how does my equipment perform? But at the same time, if I have disturbances, attacks, or anything else on either the communications network or on the device itself, or the device malfunctions, what is now the impact of this loss of data or increase in delays in a control algorithm that provides some sort of control function on the grid? So that's the overall scheme of the testbed that we're trying to implement here. And again, this is still work in progress. I'm going to mention briefly a couple of ongoing projects that we have that can take advantage of that. But in order to take full advantage of that, of course, a piece that is currently missing and we're working on is we need a detailed model as well of the communications grid that does all these data exchanges in New York to make this testbed even more realistic. And this is a very simple sample, again, of that at a very high level represents the PMU data networks that exist at the NIPA system. So NIPA has about 25 PMU systems across different locations in New York. And this represents the flows of data that exist. But essentially, these are the type of networks that we need to develop to a realistic level of detail to make this testbed even more realistic, not only from the electric grid side, but also from the communication side. Now, a couple of projects that are of interest and they fit in this time frame, and both of them are projects that do in collaboration with the Electric Power Research Institute. EPRI has been a close partner in this effort from the very beginning, and they do have also, we do have a close collaboration in our lab environment. So they have actually people who are using the lab and people who are actually permanently stationed in the lab. There is one person who is actually located in our facility and takes care of a lot of the work that is being done in the lab. So this is an example project that is actually ongoing, and it looks again at the design of a wide area oscillation damping controller. And it had several phases. This is done in collaboration with EPRI and University of Tennessee, actually, and NIPA is participating, as well as Terna from Italy are participants in this project. The idea is fairly straightforward. We want to design a controller that looks into multiple locations of the grid, and in this particular case, takes measurements from PMU angle measurements from multiple locations on the grid, and tries to detect oscillations that are happening in the grid and act to damp this oscillation. So the key idea here again is that this does receive data, PMU data from multiple locations on the grid. And again, at the beginning of the project, there was an initial design using a small-scale test bed for that controller. But then the idea is to demonstrate that on the New York State grid system, as well as in the Terna system. And that was something that was actually done earlier this year, back in January, when we brought in the control design in our the controller in our lab. We did run simulations with hardware loop simulations of our grid and of the Terna grid as well. We did use actual PMU devices, so we streamed data to a PMU device, and then this data went to the controller, and the controller again sent the control signal back to specific actuators on the grid, and then demonstrated that it can dump the oscillations. However, one thing that was missing from that initial demonstration, and it did seem from some testing that we did that it could play an important role, is that if we're talking about the wide area scheme, this data is not readily available from the PMU to the controller as if they're sitting on the same network, which was the initial testing that we did. So the next phase that we're looking now is, can we create a model of the communications network between the nodes that we get measurements from the PMUs, and then try to see how the performance of the communication network will affect the damping capabilities of the controller, either in terms of delays in packets reaching the controller or in terms of missing data from the PMU stream. So that is what we're currently working on with EPRI, and that is a good utilization and demonstration of that test bed environment. Along similar lines, the next project, again, it's a project that is being done with EPRI, a little bit simpler than the previous one in the sense that it doesn't include the closed loop system. But this looks essentially in the synchrophasor data quality and how we can fill in essentially missing data in a more sophisticated way from a PMU stream. And again, the idea here is pretty much similar, that we are going to use our test bed with a grid emulator, emulate PMU measurements leaving the grid, and then use a communications model in between to corrupt the data in ways that are realistic and expected from a communications network. And in the end, this data will reach the phasor concentrator essentially, and this conditioning module will try to fill in the data that was dropped. So that's another project that we'll be using our facilities to do a demonstration for how this will perform. On top of that, and that's a little bit of more generic slide, but essentially this environment, we're using it for a variety of projects and use cases. And as I mentioned from the very beginning, we're open also to any ideas for collaboration. We do have projects that are ongoing or ideas that we're investigating in various areas, either looking into equipment configuration and testing, looking into doing some testing for novel protection schemes before field implementation. Typical example that we recently completed is testing of traveling wave protection scheme. We are looking at that the New Park Authority to have a field pilot demonstration, field pilot implementation of a traveling wave-based scheme. So we wanted to do some testing beforehand in a lab environment. Applications of C6150, this is a substation. This is again an area that we feel that we have capabilities and we can work with others. Distribution automation and DERMS. Again, this is not strictly related to our core business because we don't have a distribution grid. But like I said, as a state entity, we do invest technologies that will be beneficial overall for the industry. And of course, cybersecurity, I did mention all the test beds that we're trying to put in place. And I alluded to it at the very beginning. This is just the beginning of building these capabilities and these facilities. If we see value, then our plan is in the next 2 or 3 years to actually invest in building an actual research center that will be this open collaborative environment that we can have many more capabilities and work more closely with other entities. Now, this covers this advanced innovation, grid innovation lab for energy, and what are the activities that we're doing there, trying to test and do R&D work in the cyber physical domain. Before I finish my presentation, I'm going to spend a couple more minutes discussing how does NIPA now bring some of this in the actual operations, that is, go beyond the testing and R&D phase. And what I'm going to talk about a little bit is our Integrated Smart Operations Center, or ISOC, and how we feel that this is something that actually takes this notion of cyber physical interdependency and into a practice and views that from a practical perspective. This is again another initiative that started about 5-6 years ago as part of our grid modernization initiative. And this center was built at record time, within like a year or so. The idea originated as an asset health center. So what we wanted to do is get data from all our assets in near real time or quasi real time. Not only data from available sensors or available monitoring systems, but also install new sensors that we think this data will be useful. Bring all these, and when we talk about assets, we started from generating plants like generators, turbines, transformers, and then moved to substation equipment. We're even looking for data that may be coming out of like transmission lines and right-of-ways. The idea is to bring all this data into a single location, and then by using various data analytics techniques, try to get a better idea of the actual health of the equipment, and try to essentially in the long term capture potential failures that we can see ahead of time without expecting and waiting for the equipment to fail, as well as potentially re-evaluate our maintenance practices and move to something that is more like a predictive maintenance as opposed to regular time-based maintenance. So this by itself was an idea that would provide value, and it's something that is fairly common amongst utilities. There are many utilities who invest in this kind of centers, and they do see value by doing this asset performance monitoring as part of an asset management plan. However, what made it took us to the next step, in our opinion, is that this idea expanded when we started designing this to not only cover the asset health of an equipment, but bring together in this same space and this same center, not only the people who are looking at the data and try to figure out what's the asset health of the equipment, but a series of other groups that we thought would provide monitoring of our grid and of our assets from a more complete perspective. One quick thing that I forgot to mention at the beginning and I need to make clear is that this center is purely a monitoring and diagnostic center. It's not our control center that does the actual operation of the grid. This is a different facility that exists in a different location. So what I'm describing here is like a monitoring and diagnostic center, but not the traditional control center. So what we did is we brought along in the same center the communications monitoring network management capabilities. So we brought our NOC into that center as well. On top of that, we brought our cyber security team and our cyber monitoring systems into this center as well. And in the end, we also brought our physical security systems, video, camera feeds from all our facilities into that same space as well. The idea was that by using this integrated view, we manage not only our physical assets, but our cyber assets at the same time. and we can exploit interdependencies in the data that we see, or we can do correlations that other ways we would not see if we had 3 or 4 different centers located in different places with little interaction between them. So again, the end idea here is if we see some anomaly and if we see that something doesn't look right, then we have the capability to check it from multiple different aspects. Is it really that the asset has a problem and is not performing as it is expected? Is there something wrong with the communication network that brings us the data, and therefore the data that we see may not be what is the real data from the asset? Do we have any issues with cybersecurity, that something has been compromised and therefore that may be causing what we're seeing? Or is there some other physical thing, like, I don't know, a fire next there, or somebody has intruded the substation that may be causing what we're seeing? So the idea again is by having this integrated view, we can make better decisions and more informed decisions. And we can at the same time, like I said, see these interdependencies between physical systems and cyber assets at the same time in a single monitoring center. And we do think that this is something that actually brings this monitoring to a next level and can provide many more capabilities. Again, this is not a vision. This is an actual center that has been operational for the past 2 years. Pictures are actual pictures from the center over here. And we have seen so far quite a bit of value. Of course, I have to admit that unfortunately during this COVID period that people are working remotely, although everything was kept operational, this interaction between the various groups was not as close as it was when the groups were physically located together. So this concludes my presentation. I hope it was useful for most of you, and this is my contact information. I will be more than glad to answer any questions, but if you need any more clarifications or if you have any other questions, feel free to reach out to me and follow up. Again, I would like to thank you all very much for attending, and thanks, Harry, also for inviting me.
Thank you, George, for the exciting presentation. Very informative and very nice work that NIPA is doing, adapting to the changes of power grid operations. Everybody can unmute themselves and ask questions. I will go ahead and ask you one question related to the last part of your presentation, the ISOC Center, and connect it a little bit with the agile testbed environment that you have there. Is any of the data that you are collecting through this kind of read-only capability from the ISOC Center related some part with the agile environment? Do you use data from the grid back to the testbed environment in the agile testbed?
It's an excellent question, Harry. And the quick answer is that at this stage of agile, we are not. But the vision is that this interconnection between the two can be something that we can work on. For the real-time simulation environment, there might be some correlation in terms of using some of the data that is available to the Agile to drive some of the simulations that we may be running for some more specialized cases. But if we look at the Agile, if I go back to the first slide, for example, they talked about the vision for Agile. Yes, we started now from doing the real-time simulation capabilities and some of the T&D applications or cybersecurity activities. But when we start moving to all the other areas like sensors, grid automation, and so on, then the relation between the two will be more clear. Meaning that we want a new sensor to be installed that will feed data to the ISOC. We can first test it in Agile before we deploy and see the value before we deploy it. We want to use some of the data that is in the ISOC to test some new application that we are running. Yes, this is possible. A quick connection that may exist is PMU data. I mean, we can easily bring PMU data now both to the ISOC and to the Agile, and that could be the first connection because we don't use PMU data yet for real-time operations. So we are actually looking into potentially using them for some of the asset management or asset monitoring activities as well, and see if we can get some value from there. So this would be something that, again, can be shared between ISOC and Agile. But the vision, again, would be exactly what you described, that this can be interrelated and technology that can be first demonstrated, developed, or tested in the Agile lab eventually can find their way into the ISOC.
I see. Thank you, George. Thank you, George. There are 2 questions in the chat. I will ask these questions. If anybody else has any other questions, can unmute themselves. I see Sarajis, if I say the name correct, ask if there is any way to detect the presence of malware in the intelligent electronic devices. For example, he provides this argument that, you know, a newly purchased intelligent electronic device may come with a malware. So do you have any procedure in place in order to test these devices before putting them either in the actual grid or at the testbed environment?
Again, it's a very good question and very relevant. It is an area that we're working in the lab. This is something that our cybersecurity is leading, and they do have some processes in place that look into supply chain management and how do they do some of this. I think they're using some fairly simple techniques now, static type of techniques, either looking at hashes or something like this. We don't have a strict process now for the Agile itself, because again, if it's something to go in the field, there is a process for that, and we can adopt the same process for Agile. Actually, we are looking into establishing some procedure now of how do we bring a new device into the lab environment and what kind of tests we would like to do before we connect it to a lab network. However, we do participate now in a DOE-funded project with a couple of other partners that actually is looking at exactly this. How do we develop new ways to detect and identify and analyze malware, using also artificial intelligence, machine learning type of techniques. And as the end of this project, there will be some sort of process developed and some sort of software developed that if you get a new device, you can take the firmware of that device, run it through that system, and it will give you an idea if this is a real firmware for that device or something has been compromised. So we don't have the capability yet, but this is an area that we are working on. And like I said, we're actively participating in the project that looks exactly this aspect.
That is very interesting because, you know, firmware running externally on other device and emulating is a very difficult task, and the outcome of the project should be very exciting. Another question has to do with the modeling of the distribution system. If he's considering the cyber-physical impact of distributed energy resources.
Very good question again. Thanks for that. I will have to preface that with the fact that, of course, whatever we do, we are open to do modeling of both distribution and transmission system. However, given the fact that NIPA is a transmission company and we had to start from somewhere, we decided to start from the transmission system because we had much easier access to data and it was much easier for us to develop the initial models. But to expand on that, yes, we are looking and we are having discussions with other entities, other utilities in New York that actually do have a distribution system to see how this can be incorporated into potential future models that we have. And at the same time, we do participate in 2 projects again with external collaborators, April being one of them, and both of them are funded by DOE actually, that looks into DERMS systems and distributed energy resources and impacts and interactions between distribution and transmission. And as part of these projects, some of this work will be incorporated. I'll give you a high-level idea there. What we're looking there is, again, exploiting co-simulation environments that we can use, potentially a real-time simulation environment for the grid, a real-time simulation environment for a specific region of the distribution system that we are connecting DERs, and then having some simpler simulation in between that represents larger scale distribution feeders and potentially larger scale transmission grids. So again, looking at the hybrid approach that will include also hardware in the loop and core simulation that can explore some of these.
Thank you, George. And another question has to do with if you have released any open source software or any part of the simulation model, maybe sanitize, anonymize some of the parts to the community, or if you intend to do such a thing.
For open source software, no, we don't have anything developed in terms of software that we can release, so that we don't have something in this area, at least not yet. For the models, we are still kind of like into thinking how we are going to do that. There are a couple of challenges there. One is what I mentioned at the beginning, that we are trying to do everything on the New York State grid model, which does make sense, and that creates a very good test bed. But we don't own the whole New York State grid model. So we are relying a lot on external entities providing data for us, and most of the time this data is considered confidential CII data. So we try to keep them confidential to make the people who give it to us or will be giving to us confident and able to release them to us. We do have processes, however, that we can allow people to use these models, maybe via some NDA or something, and use this model if they need to. Sanitizing it and creating some simplified versions is something that we have thought about it, but have not done much work on that yet. But it could be something to look further into once we get some more experience on the model development and how we can reduce these models in a way that sanitizes them and also keeps them useful for others to use. So the immediate answer is no, but it's something that we could consider and see how we could do it in the future. The other aspect of it is that for some of the work that we're doing that we may not want to use the entire New York State model, we may, as part of specific projects, develop some more simplified test beds that can originate from some components of the New York State grid model and then simplify them to something that is still useful, but is not the actual data and then can be shared with others. So we will still look into it, but we don't have anything right now.
Thank you, George. Another question has to do with the communication network. I don't know if you are able, if you want to share this information. Do utilities or specifically NIPA utilize, communication networks such as AT&T's or Verizon network, or it runs on a totally separated communication network?
It's an excellent question, and I can address it because that was part of my previous job at NIPA, actually. So I can talk about it a little bit. And that's actually a very good question because it also brings up some of the challenges for the communication infrastructure and some of the approximations that need to be made. Currently, no, utilities and NIPA as well use third-party services. So we may have redundant service, we may have multiple paths and so on, but the networks are on third-party networks that we lease services from. They may be dedicated, but still operated by third parties. However, again, as part, and I actually had a slide on this presentation, but I took it out so that I don't distract the discussion. As part of this, again, grid modernization initiative that NIPA originated, there is a large project that we are undergoing now, again, started about 4 or 5 years ago, which we call Communications Backbone, that looks into deploying NIPA private communications infrastructure. So, and that will be also something that we can more easily model on our network, on our model, because we do have all the information for that, and it will also be more meaningful to have. So NIPA is looking, and it is an ongoing project. We do have some implementations already done, deploying OPGW fiber on most of our transmission corridors. We're also looking into leasing dark fiber for areas that we don't have transmission, but we do have facilities, and utilize that to bring data back in and use this as our primary network. Lease services will still be used as a secondary network, and then we have a tertiary network that we're putting in place or expanding actually, which will be a microwave-based network. And all these three options can be to some extent modeled as well. But yeah, we're looking at these three layers essentially, and the fiber deployment is ongoing, microwave upgrades and expansion is also ongoing.
Thank you, George. Another question. I think we have a few more minutes for more questions. There is a lot of started a lot of questions in the chat. So one question coming from Juan Ospina, it has to do with the co-simulation. I think you briefly mentioned that you do some co-simulation not only between the electrical and the communication domain, but are you planning to also expand on that using also other parts like thermal, water, and gas simulation, and how this will interact not only with the electrical but also with the communication part of the modeling and simulation?
Again, very good question, and thanks for the question. Immediate answer is no, we have not looked into it at this point, and it will be a significant undertaking. However, I must say that this is the vision of my boss, who is a mechanical engineer, so he is interested in co-simulation of this nature. So one of the ideas that he brought up is gas infrastructure, because gas infrastructure has a significant impact on the grid as it is now, until renewables get a much higher penetration. So it has been brought up as an idea. but we have not practically looked into it yet. Like I mentioned, this is the vision of our SVP of Technology Innovation, who is my manager as well.
Thank you, thank you. And following on that, the other question is still on the communication part and the co-simulation. How do you decide, and what are the important variables or components that you co-simulate on the communication network in the co-simulation between the electrical, the physical layer, and the cyber communication layer? How do you choose all these devices that are co-simulated in the communication network?
Yes, for this, I probably don't have a very good answer because much of this is still work in progress or being thought of. I mean, the high-level answer would be that at the beginning, at least, we may start doing some of this on a case-by-case basis. So looking, for example, at another project that I mentioned, like the oscillation damping controller. The way we tested the controller was that it receives data from a couple of specific locations in New York and uses these phase angles as input to create the control, to implement the control algorithm. So for that particular project, for example, the idea will be to investigate what is the path for this PMU data, we're looking PMU data there, to get from these locations to where the controller is supposed to be. This can then be investigated with NIPE-IT and see how much information we can have to build a model of that path. Again, fact that this might include third-party providers that are engaged makes a lot of things need to be approximated. But that would be the starting point. That is, do it on a case-by-case basis on what data you need and what information you can collect from that communication path. To do it in a more holistic way, this will be quite challenging and will need a lot of thinking from our side, especially given the fact that communications modeling is not something we normally do, most of our power engineers. Yeah, this is a question that I cannot answer any better at this stage.
Okay, thank you, George.
And one thing I would add to this, it is quite complicated because some of these models can be quite sophisticated. Yes. You can specify equipment and you can specify a lot of parameters of this equipment, which might be difficult to know what they are in the communications network.
Yes, thank you. And the last two questions, to answer them a little bit quickly, so and we wrap it up. I see a lot of your reminders are popping up for the next meeting.
Okay. I did notice them, but thanks.
Yeah. So what is the target range here? At least Nicola was asking this question. What is the target range for of DER's contribution in the energy mix of New York's power system, and how much do you expect Agile to boost such targets?
DERs, I don't know, to be honest. I can't tell to at least, but New York has set targets that are for renewable energy, and they are quite aggressive, actually. I don't know, some of you may be familiar with them. They don't specify if that renewable energy, solar, for example, can be behind the meter or can be grid scale. It can be both. And I would speculate that a significant number of it will be behind the meter. There are some studies and some estimations that have been done by the New York Independent System Operator. I don't have numbers on the top of my head, but if I look at overall targets for renewables, the target is, and actually I did have a slide that I again removed because I thought this might not be that valuable to put it in there, but let me bring up on the side another presentation that I have, one slide that talks about it actually, so that will give you a little bit more accurate numbers. But looking into renewable penetration, there is a target of 6,000 megawatts of solar in the next 5 years by 2025. So we're looking about 6 gigawatts of solar in the next 5 years. We're looking about 70% energy coming from renewables in the next 10 years by 2030. So there is a 70 by 30 goal. So we want by 2030 to have, in terms of annual energy, 70% coming from renewables. And there's a storage goal as well that looks at 3,000 megawatts of storage by 2030. And then by 2035, we're looking at 9,000 megawatts of offshore wind. Keep in mind the peak load for New York State grid is about 30-something gigawatts. typical load is about 20 something gigawatts. So these are quite aggressive targets. So 9,000 on a 20,000 load, normal load grid is 50% or so in terms of installed power capacity. And then there is a goal for carbon-free electricity by 2040, which is quite challenging, and we'll have to see what this entails and how this is going to be implemented. Now, how the lab can play a role in this, that's actually a question that is being discussed now. From our point of view, NIPA's point of view, we think that this will be useful, and it will be a venue that can be used either to perform some of the more sophisticated, non-traditional type of studies that we may need to do. Actually, don't worry about these notifications, they're not that important. Or it can be used as a test bed again to vet and evaluate technologies that can be used to support this type of wind or solar integration. So it is an open question that we're discussing with various stakeholders. Our plan is, if we show value with what we have, it will be much more valuable if we move to the next phase and build an actual facility that then can be more powerful and have a significant impact on all these goals.
Thank you, George. I think very good numbers there, aggressive, but hopefully they will be achieved. And the last question, I think it was answered, but I will ask it again just for the sake, and we wrap it up. Essentially, you mentioned that ISOC is a monitoring diagnostic center, and if I remember correctly, it does not interact at all with any control center. And this is the question from Jim, just to make sure that my answer to that is correct. Right?
Yes, it is correct. Okay. The interaction is, of course, on a human-in-the-loop basis. So yes, people talk between the control center and the ISOC sensor, but there is no currently direct interaction between the two. The only interaction that I'm not quite sure if it was put in place or not is that there are views of some of the ISOC application from various other facilities of ours, as well as our control center. So the control center can see some of the ISOC information, but normally not the other way around. Because some of the more real-time decision-making information is more protected, and not everybody in the ISOC may be allowed to see it.
Thank you, George. I think we're a little bit over time. Thank you again for giving this very informative presentation and webinar. I would like also thank you everyone that joined this presentation. It's been recorded, and we will post the recorded presentation on our website. I shared the URL in the chat. Thanks again, George, and hope everybody stays safe. And we will follow up with more presentations in our email listing of our task force.
Thank you also again very much, and thank everybody for attending.
Thank you, George. Bye-bye.